Okay, so what we want to do now is take a look a little bit from the more theoretical point of view, from our knowledge of gravitational force and circular motion. We want to take a look at the dynamics of stars rotating around a galaxy, right? So if you imagine the galaxy as this object that has this very dense core, and then in the outer regions of the galaxy, there's stars. I mean, there's stars everywhere. But we want to make a difference between what happens inside this more dense core and what happens outside in the outskirts, if you want, of the galaxy. So if you imagine one galaxy here, that red point is a galaxy. That galaxy, sorry, not galaxy, a star. That red point will be a star. If you imagine a star, sorry, outside, that star will be affected by the gravity of this center, this dense core in the middle of the galaxy. So we can do a very simple analysis of circular motion there by just applying the usual net force equals mass times acceleration. The force will be the gravitational force, right? And the acceleration will be the centripetal acceleration of that star. Where this m here will be the mass of the star. So the force of gravity, the gravitational force, sorry, will be gmm over r squared, being r the distance from the center of the star to the galaxy, so that green line over there. Big M will be the mass of the galaxy itself, or the core, the center of the galaxy, and then small m would be the mass of a star. Now that will be then equal to the mass of the star times centripetal acceleration which will be v squared over r from our knowledge of centripetal acceleration. This radius will cancel with this one. This mass will cancel with this one, right? And what we get in total if we solve for v is that v will be equal to the square root of gm over r. So that is, well, basically telling us that v is proportional, that v is proportional to 1 over the square root of r. What that means is that outside of the galaxy, the expected behavior, if you look at the variation of velocity with radius and you graph this, that's going to drop like this, more or less. So what you would be expecting is that outside of the galaxy, in the outskirts of the galaxy, the expected behavior is that the velocity drops according to this model here, right? So this doesn't work for inside, so that would work only for outside of the core of the galaxy. So if you want, what we have at this point is this. We have knowledge from this analysis that we don't know we don't know how things are gonna work inside, but what we know is that outside we should be looking at, so this is how it should look. I'm not drawing anything in here as a solid line because we're unsure about how that happens inside. Everything we have is a model that describes how things happen outside, which is this model here. And that model here, if you just look at it from the radius of the galaxy, or sorry, for a radius outside the core of the galaxy, then this is what you are saying, right? That's, if you look at the slide number 12, that's like the second half of the graph. So we're still looking at what happens inside. According to this should be going up, but that's not entirely true, because if you go inside the galaxy, then if you go inside the core of the galaxy, then the gravitational force is not this simple, right? It gets a little bit more complicated, and that's the next thing we're gonna see. Okay, so oops. So we're left with, okay, give me a second. Okay, for some reason I lost the page that I just did, but it's in the video, so that's not a problem. So we were saying that we're left with a graph where we know what happens outside. We don't know what happens inside. And outside, the behavior is like this. It drops somehow. And we're looking at what happens inside. Now, to understand what happens inside, we need to have like a different model in mind. So we're looking at what happens inside the core of the galaxy. You can imagine that core of the galaxy like a very big, obviously, and dense gas cloud with, we're going to assume a constant density. So what we're looking at is if you're inside at a distance r from the center, so if you're at this point, what would be the expected behavior of your velocity? So it's actually not that complicated. What we need to understand is basically this. When you're at this point, the only mass that is causing a gravitational attraction on you is the mass inside this imaginary sphere. So if you're at this point, let me just put it in a different color. So if you're at this point, right, at that point, then only the things that are between you and the center will cause a gravitational attraction. If you're outside, say if you're here or here or here or here, so if you are at this point, at the red point, then all of the things outside that sphere will actually not cause a gravitational attraction, or better, let's say that they will cause a gravitational attraction, but altogether it will cancel. So at the end of the day, what matters is the amount of matter that is inside this sphere for the amount of gravitational force that you experience. Everything outside that sphere is not important. Now, the question is, how much mass is there inside that sphere, right? So, well, the density of this whole core of the galaxy, we're going to say that that density is constant, is equal to the mass of the whole galaxy over the volume of the whole galaxy. And because the density is constant, the ratio mass over volume for the whole galaxy, or just for this shaded region that we've indicated here, will be the same. So the mass of this and the volume of this will give me the same density as the whole density of the galaxy. So what I can say is that the density is equal to the mass of the galaxy over the volume of that, which will be 4/3 pi r cubed. So if you rearrange this, you're going to get something like 3m over 4 pi r cubed for the density of the galaxy. So what we are left with is an equation that says that the density of the galaxy can be written as 3 times the mass over 4 pi r to the power of 3. Now remember that the whole point is to know what is the amount of mass inside this sphere, this shaded area, because that's the mass that matters for the gravitational attraction. So what we get is that that amount of mass will be equal to 4 pi r cubed times the density of the galaxy divided by 3, right? and that is the density, and that is, sorry, the amount of mass inside the galaxy. Now, we can go back to our previous analysis, and in that previous analysis, we found that for a point outside the center of the galaxy, the velocity is equal to the square root of gm over r. That's our previous result, the one that describes the drop of the velocity. And we can apply that here. Why can we do that? Because we're looking at this particular point, the point right on the edge of that sphere. So it's like you're looking, oh, sorry, what happened there? This is mass over volume. So we're looking at the point that is right at the edge. So it's the first point outside of the center, so we can still apply this. Just to emphasize the following, the whole idea here is to use this result that we obtained, but to include there the fact that when you're inside the galaxy, how far away you are from the center determines the amount of mass that you have. So in our previous analysis, this mass always represented, this mass always represented the mass of the whole galaxy. But now in our analysis that we're doing here for what happens inside the core of the galaxy, that mass is not the mass of the whole galaxy, it's just the mass contained in this imaginary sphere when we are at a distance r from the core. So we're going to use this result here that we obtained, but we're going to include the fact that the mass is no longer the whole mass of the galaxy. So the velocity of a point outside or right at that point will be equal to g times m, but then m is going to be this whole thing. So that mass will be 4 pi r cubed times the density over 3 times the radius. That's what you get. Okay, or well, you could actually have it just over 3 here and then over r here, but it's the same thing at the end of the day. So when you rearrange this, and I'm gonna just end up writing the same thing that I had before, I'm just gonna do it like this: g 4 pi r cubed times density over 3r. And when you do this, you get this to cancel, and so this r cubed will go into r squared, and what you get is that the velocity will be actually equal to the square root of g 4 pi density over 3, right? g 4 pi density over 3, yeah, that's everything. And then the radius squared will be affected by the square root, and you get this times r. So what you're saying is that the velocity of the rotation velocity of a point that is at a distance r from the center of the galaxy will be given by this, which gives you a completely different description, where the velocity while you're still inside the core of the galaxy will increase linearly with a gradient equal to this whole thing, g 4 pi density of the galaxy, which is a constant over 3. Now, what happens when you put those two things together? We have basically something that says v is proportional to 1 over the square root of r. That's outside, and we just found that v is proportional to r inside, right? So this we know has this type of behavior, and this we know has this type of behavior. So if you plot a graph that tells you what happens inside and what happens outside in terms of the radius from the center of the galaxy, the velocity will behave initially increasing linearly. So let me just draw a line here to separate inside from outside. So inside it will behave like this, increasing linearly, and then after that increase, you will that's this increase, you will go with the second one, which is telling you that this drops like this, which is consistent with the graph that we're getting for the expectation. So this is the whole process to get to the expected graph of velocity versus radius for the speed of rotation of stars around the center of a galaxy. What's the big deal with this? The big deal is that, well, when we look at that velocity versus radius, we're getting this, yes, but then we're not getting the drop. We're getting something that goes like, oh, sorry, that goes like this, which is very surprising. Let me just, okay, there's no evidence that I ever said that. Good. So that's it, okay?